Hey, welcome. So what I like to do here is kind of do a video that's a little bit different than just like solving problems. And this video is really to kind of work on some misconceptions that a lot of us kind of take when we are learning about different parts of functions. So what I'm going to do in this example or this video is really kind of cover some misconceptions of characteristics of functions. And I'm going to do that by providing you with a statement that I'm going to tell you is false. So rather than asking, is this true or false? I'm saying, hey, these are false statements. But what we want to do is provide a counterexample showing that it's going to be false. So let's get right into it. The first one is saying all functions bounded above have an absolute maximum extrema. Well, that kind of sounds, correct here. If we're looking at, a graph, if it's bounded above, that means it doesn't go above a certain value. But is it actually an extrema? And that kind of comes into the definition of a absolute maximum extrema, basically meaning the highest point in the graph where every point to the left and to the right is going to be below that. So if we were to graph something here, let's say we looked at something that is the highest point, but instead of it actually being a point, it's a hole. So therefore, if this was filled in, then yes, that would be an absolute maximum extrema, but it's a hole. So it's actually not defined. So therefore, the value here is not an absolute value extrema point. This is bounded above, though. It does have an absolute maximum value. You could talk about how it has a maximum value, but it's actually not an extrema. Another example here is if we were dealing with something that had like an endpoint. So this could like continue or it could be bounded. So this is an example of a function that's bounded below and bounded above. It has a maximum value, right, just like it has a minimum value, but is that actually an extrema? And if you remember, endpoints are not extremas because it doesn't follow the definition of an extrema where every point to the left is below as well as every point to the right, because there are no points to the right on this endpoint here. So therefore, these are two counterexamples, or these are two counterexamples that is going to show that this statement is false. The next one works on is that all functions that contain a discontinuity are not defined for all x. And this one, once we kind of work with discontinuities, we kind of work on a lot of different examples. We work on holes and asymptotes. So students get very familiar with, there's a discontinuity, that means it's not in the domain. But we got to remember that, especially with piecewise functions, a lot of times we're dealing with two functions that have a discontinuity, but it's a jump discontinuity where one value is undefined, but then just below it in the other function, it is defined. So even though this function is not continuous, you can't draw it without, lifting up the pen and connecting it to the next function, it is defined for all x. That means the domain is all real numbers. The other example that I worked at is, looking at holes. A lot of times when we look at the hole, we say, oh, it's not defined, at that value. But we could also create a piecewise function where we could say, well, we want the value of that hole to be defined, for this value. So both of these examples are defined for all x, even though they are not continuous. So two counterexamples once again. The next one says every point of a graph is labeled either as increasing, decreasing, or constant. And what this kind of comes into is really understanding how we identify increasing, decreasing, or constant. So when we're looking at a graph, what we're doing is we're looking at when is the graph basically going up and when is the graph going down. And we're talking about the intervals along the x-axis. So let's just say here, 2 and 3. So we can say from negative infinity to 2, the graph is going up, and we could say from the interval from 2 to 3, the graph is going down. But are we actually identifying each coordinate point, each x value as either up or down? And that is something that a lot of students struggle with, and because we're not defining actually the points as increase and decrease, and we're looking at the graph going increasing and decreasing. And the point I kind of bring up is that I talked about in class. If you're driving your car and you run over a nail, and therefore you start declining in speed, like the point that you ran over the nail, we wouldn't say that you are increasing as well as decreasing in there. So like for instance, a quadratic, you're, increasing and then decreasing, right? So when we're writing this, again, just remember that, at this point, let's say A, we use parentheses because we're not defining the point as actually increasing or defining the point here as decreasing. So it's not A is increasing or A is decreasing. We use these parentheses to understand that it is not including the actual value here as an increasing, decreasing, but it's more of the interval that we are going to be talking about when increasing and decreasing. So again, don't use the brackets here to include that value because that's not really what we are saying when we're talking about the increasing, decreasing intervals. The next one is going to be all functions have end behavior, and that is just not true, right? There's a couple different ways we can end up with end behavior, but it's really important to understand end behavior. If I look at a graph like this, as I keep on zooming out, that graph is going to continue going up and continue going down, right? But if I look at a graph that maybe looks like this, as I keep on zooming out, the graph is going to continue going, to the right and up, but it stops going to the left. So therefore, there's no end behavior going to the left, or as x approaches negative infinity. Another thing we could look at is if the graph is like approaching a vertical asymptote. So even though the graph is continually, as it's going to the left, the graph is approaching, and again, it can approach infinity, negative infinity, or it could actually approach another horizontal asymptote, right? So we can have end behavior going to the left, but as we go to the right, you can see that this graph stops. It's not continually going to the right. Even though it's going down towards infinity, it's not continually going to the right, so there's not technically no end behavior. And then another example that we can look at is the oscillation. So, dealing with a graph that is oscillating is actually not approaching any given value, infinity, negative infinity, or a certain number. So therefore, we'd say that it has no end behavior. All right, so those are some of the kind of basic ideas that I came up with, and these are things that I just kind of thought about before my students went and take the test. So what I would love to hear from you as far as what are some misconceptions or what are some false statements that you would think would be good to add to this list, because I want to grow this list and continue on this where it can benefit more students. So if you have a good idea based off of what I provided, please let me know in the comments, and I'll be happy to add it to the list. Thanks.